now we look at this. And so this is the algorithmic model for the descent methods. Actually, I think, yeah, it's so we start with the starting point, x naught. X naught is starting point, and given a function given a function f, which is a real value function of n variables, okay? And then first we set the iteration index k as 0, okay? Then first we determine a search direction. And after that, we find, okay, once, I think we've seen this before, at a given point xk and the search vector sk, then the n-dimensional optimization becomes a one-dimensional optimization, right? So we search along that direction. So we search along direction S to find the lambda, okay, to find the step size, the optimum step size. So lambda k here is called the optimum step size or optimum step length. Okay, so we minimize fxk plus lambda sk with respect to a scalar variable lambda. This is a light search. Okay, this is how we started. Okay, but later, then, okay, we find that, okay, and this is what we call the step length. When we do the optimum light search, the theoretic, when we implement the optimum light search, the method has a very nice property. Okay, but the thing is, but nowadays we know that with good methods, the light search doesn't have to be exact. Okay, and this is why I say that in the bracket, or at least to reduce the function f sufficiently. And we will see later what is sufficient level that we need to reduce the function f so that the algorithm converges to a solution. Here we call the inexact light search. Whereas in the process of we find the optimum step length, we call exact light search. You will see this, you will hear this, right? Let me rewrite it. This is what we call this process. And the lambda that minimizes the function f, xk plus lambda sk is called the optimum step size. Optimum step length or optimum step size. Okay. Once we know the lambda k, then we update. We update the iterate by the standard formula, which is the xk plus 1 equals xk plus lambda k sk. In any method that we use to solve optimization problems, this is the standard. Okay, we use this form of update formula. We update the iterate xk by using this form. Okay, and different. Okay, so the difference in methods is that, okay, in various methods is that we have a different way to compute the search direction sk. That's all. So you see that but okay, whatever method that you use to compute the search vector sk, we still have to need to solve a one-dimensional optimization, and this is why the previous topic was okay. The previous topic is very important. Okay, it's very important, and because if you fail to solve that problem, whatever method that you use to compute the vector S is you can't solve the problem. So the success in solving optimization problem relies on how we do the line search. Okay, that was the most important part. If you use the best algorithm, but if your line search is very bad, then the algorithm that you use to compute the SK, even a very good method, still okay, still does not work properly. Okay, so after we update the iterate xk plus 1, then we do the test. We have to check if we need to stop the iteration or we need to proceed. We need to go on. Okay, so that is for example, if we find that the xk plus 1 does not differ much from the xk, then you may decide to stop, right? Or you may see the fxk plus 1, the difference in the fxk plus 1 and fxk, right? Okay, then okay, so if we find that we need to continue the iteration, then we set the index k as k plus 1. Okay, and then we go to step 1 again to compute the search direction. Okay, and this is how you say that it has a very simple structure, right? Now this is why we look at okay, but the details in computing the S and the details in computing the line search, okay, the lambda k, it's okay, this is what we have to, this is I have assigned homeworks, okay, in which you have to do this so that you can get you can understand this, and then you can, okay, you can understand this better than just read papers in the homeworks. In the homework number 2, you will solve the one-dimensional optimization, right, on the line search. And in homework number 3, I think you will write program the Newton method to minimize the for minimization. And homework number 4, you will write the quasi-Newton. And homework number 5, you will write the conjugate gradient method. So we built up our skill and knowledge step by step. Okay, so as I said, right, step 2 is called the line search procedure. When we find a line search procedure is the procedure that we find the step length, the lambda k. Okay, there is a definition that we will refer to very often. Is called desent property. And now I will explain why we okay, first look at the definition. A search direction is said to satisfy the descent property if SK transport by FXK is negative. What is this? Now we will have to. Okay. So let's let xk is the current iterate. Suppose we choose the search vector sk. Okay. And so I better write it in this way. Okay. Now, if we once we, okay, so suppose xk and sk are given, okay, then you see that if you, now we look at the function f of xk plus lambda sk. This is a function of a single variable, right? In the variable lambda. Now, you see that when we find the lambda, if we don't know anything about the property of the search vector sk, so the lambda that reduces fxk plus lambda sk can be either negative or positive, right? Right? Okay. Normally, given a search vector sk, then the lambda can be, in general, lambda can be either negative or positive. We don't know that in advance if we don't have any information about the vector sk. Okay. Now, when the search vector sk has descent property, let's look. When the sk has descent property, what happens is this. At this point. Now, when you look at the definition of the directional derivative, what is it? The directional derivative of the function, the directional derivative of fxk plus lambda sk with respect to lambda. This is in fact equal to sk transpose fxk, right? In chapter 4, if you, okay, so the f xk plus lambda sk by the lambda at lambda is equal to 0 is equal to sk transpose fxk. Right? From chapter 4, you know this. Right? So what is it? So from the directional derivative, from the interpretation of the directional derivative, this is the slope at this point. Right? It is the slope at this point. Now you can see if the slope at this point is negative, that means when the slope at this point is negative, right? So that means if there exists a lambda, because from the continuity property of the function, when sk transpose fxk, or the slope at this point, is negative, right? That means there will be a point, okay, for which the slope, there exists a lambda such that the slope of the function fxk plus lambda sk is 0, and that point is the minimum, is a local minimum point, right? Because the sign of the derivative cannot change immediately. At this point, is 0, it is negative, right? And then before it changes to the positive sign, it has to be there exists at least one lambda for which the slope is 0, and this point is the optimum point, is the local minimum point. This is what I say lambda star. Okay, the slope is 0. Okay, and what is the slope at this point? The slope at this point is is equal to f is equal to sk transpose grad fxk plus lambda star sk, right? From chapter 4. Whereas the slope at this point is okay. Now see, okay, I'll just write it down. So if sk transpose grad fxk negative implies that here we okay. Don't forget that we in our course we assume that the function f is okay is continuously differentiable. We don't consider any general function f. So when the sk transpose grad fxk is negative, then it implies that there exists a positive lambda such that there is a positive lambda star, okay, such that oh no. By the lambda fxk, okay, right? Where lambda is equal to 0 is equal to sk transpose grad fxk, then fk transpose okay is negative implies there exists a lambda star such that the sk transpose equals 0. Okay. So this is the okay, and this is the okay. So you see that what happens when we know that the directional derivative of the function f at the point xk is negative, then that means the line search okay. Then when we find the line search, we know that the lambda we are looking for is positive. Then we search only half of the real line instead of the whole real line. Then it's much easier. If we don't know anything, then you have to do some tests. But if we know that the lambda that we are looking for is positive, then we search along the positive axis of the lambda. Okay, and that's simplify the search procedure considerably. Okay, and there is a function. Okay, in nonlinear optimization, we use a quadratic function. Okay, sometimes we use a quadratic function as a benchmark. Okay, quadratic function is a very simple nonlinear function. Okay, if we cannot solve if we cannot minimize a quadratic function efficiently, then the method shouldn't work for other nonlinear functions, right? Because this is probably the easiest. This is a very easy problem in nonlinear minimization. Okay, in optimization, and for quadratic functions, we know analytical solution. When we know analytical solution, then very often some people use this as a benchmark or the test function. If your method cannot, but you will find later that if your method can minimize the quadratic function, it doesn't mean that the method is good enough. At least this is you have to be able to the method has to be able to minimize this, okay, before doing other jobs. And that's one reason. And the second reason we consider quadratic function is that in many applications, you'll find that especially those applications concerning energy, and you will see that the quadratic function often arises. For example, in power system, if you find the transmission loss, you will find that the transmission loss can be written as a quadratic function. Okay, now with the quadratic function, fx is equal to 1/2 x transpose qx plus p transpose x plus r. R is a real number, p is a vector, and q is a symmetric matrix. Okay, and we know that when q is positive definite, then the function f is convex. From the homework from homework number 2, you will see that I think in the homework problem 1 and 2, from that you will see that we use the result to show that when q is positive definite, then the function f is convex. Okay, for quadratic function, if q is p positive definite, and when we find the gradient, we find that the gradient of the quadratic function is qx plus p. And the second derivative is the, okay, when we apply the definition of the gradient vector and the H matrix, then you will see that the gradient of f is equal qx plus p, and the H matrix of the function f is equal to q. Okay, and from this, then how can we find that the minimizer of this function? When the minimizer of this function is, what is it? You see, when q is positive definite, what is the consequence of the fact that q is positive definite matrix? Q is positive definite. Okay, Q is positive definite if and only if all its eigenvalue are real numbers and positive, right? And determinant of the matrix Q is equal to the, as we know, the determinant of a matrix can be expressed as the product of all eigenvalues. So when all the eigenvalues of the Q matrix are positive numbers, then that means the matrix Q is non-singular, and therefore Q inverse exists. Okay, and so when we find that, we apply. So when we apply the necessary condition, applying first order necessary condition theorem, okay, we have the that f extra equals 0, then we find that Q extra plus P is equal to 0, right? We set the gradient to be 0 to find the minimum, and you will see that there is only one x star satisfy this the gradient condition. Then that means that therefore x star is unique and equal to the minus Q inverse P. So this is the minimizer of this function, and this is unique when Q is positive definite. If yes.
Professor, can you hear me?
Yes.
I just want to clarify one thing, that in the
Sorry.
quadratic form.
Let me finish this first, okay? Please don't interrupt. You can ask me later after the class. Now we go to the steepest descent method. Okay, but the steepest descent is the simplest descent method. Okay, among descent methods, this is the steepest descent is the simplest one, and it was invented by Cauchy in the 19th century. And this method, okay, and variations of descent methods are used in many applications. For example, in the I think in machine learning, you may hear of the word the gradient descent method. Okay, the gradient descent method is just a variation of steepest descent in which we fix the step size. And the people try to, people try to implement the method in a very simple way, but in my view, I don't think this is good, because there are better methods than that. But of course, you need to invest, you need to put your effort in studying to learn some new methods or the technology. If you use this method, then and the gradient descent method takes a very long time. It converges very slowly. Why? Because the steepest descent has a linear convergence. If you after this course, you will see the steepest descent has linear convergence rate of linear rate of convergence. So it is not fast. And then if you even with the optimum line search, then when you implement it with a fixed step size, then the performance is even worse. right? And how can you expect good result from this? Okay, linear convergence is not bad if you know that the rate constant. If the rate constant in the problem you are solving is near zero, but if you don't, but if that is not the case, then the steepest descent converges very slowly. And so sometimes I think, yeah, I think many years ago there was some students in a lab. I don't mention the name. They solved this in what we call the image resolution. And they used the gradient descent, and it took 3-4 days. And then I think they have to run the computer in the lab 3 or 4 days just for one problem. And that was, but then I supervised a master student in the lab, another student, and I suggested him using a better method. And he can solve that within a couple of hours. Now you can see the difference between the 3 or 4 hours. And that was done by a PhD student, and I was astonished. Okay, and then, okay. Now, okay, so what is the steepest descent? The steepest descent is, the steepest descent computes the SK with this formula. So you see, it's very simple. The SK is equal minus grad fxk. So once we have the gradient, then we multiply that with the -1, then we have the search vector. So we search along we search along the negative direction of the gradient vector. Okay, now we'll see what happens here if we do this. And so in this proposition, assume that we minimize a function f, okay, and in every search direction, okay, then we have the fact that in every search direction generated by the steepest descent method, okay, well, there is a descent property. So that means every SK generated by the steepest descent method has descent property. So what does it mean? It means that when we use the steepest descent, right, the lambda is guaranteed to be positive. The lambda k that reduces the function f has positive value. It cannot be negative. Oh, no, sorry, let me say this. When we use the steepest descent, we minimize a nonlinear function f. At least we know that there is a small lambda that reduces the function f in that direction. A positive small value of lambda. Okay, I mean the local search. Because when the function is non-convex, then okay, things can happen like this. Just give you an example. Oh. For example, like this. In this function, right? You see that this, okay? This is the slope at this point. This is the SK transpose fxk, right? It's negative. So when the S transpose fxk is negative, it implies that there is a small lambda such that fxk plus lambda sk is smaller than fxk. This is what we know. Okay. Now, if we search, and this is, you see that in practice, if you want to find a global minimum in the direction of the vector sk, it takes a lot of computation, and it's not worth doing this. Okay, if you find a local minimum, and if you choose, okay, the method will converge into the point. That this is the idea of doing iteration. I think in real, I give you an example of real life. In real life, we cannot. If you want to do if you want to do a perfect job, you cannot do it only once, right? You have to do that and improve it, do that and improve it. That's the idea of doing iteration, right? For example, let's say if you write a report or a thesis, right? You cannot write it in a perfect, okay? You cannot write a good thesis only in one iteration. You need to do that many iterations, because as you write it, and you'll see that, okay, if you expect to write a very good thesis or a good paper in one shot, I think it's impossible, because I cannot do this, and my professors cannot do that. I think we do that, and we improve that. That's the idea. As we do the iteration, or as we write it and improve the paper, then we understand. Sometimes we understand what we are writing better than before, and then we improve it. Okay, and this is how life evolves as well. Okay, just give you some the philosophical something that is rather philosophical. Okay, now we come back to this. Okay, so we know that when you say that the advantage of the steepest descent is that it guarantees that in every search vector, okay, the vector sk has descent property, and therefore when we do the line search, you just choose a very small lambda, and then it will reduce the function. And then if you keep doing that, the cost function f is reduced, okay, in many times. And so we hope that eventually we will have a better design or a better value of the function of the, okay, we will achieve at the minimizer. Okay, now, okay, then let's see. In this example, okay, let's just go to this example. Okay, just skip this. I think this can be skipped for the moment. Now we come to look at this example. In this example, we consider a quadratic function. You see that when we okay, the function when the function f is quadratic, we know the minimizer x star analytically, right? By the formula x star is equal minus q inverse times p, right? Now here I will show you that when in the line search, when the function f is quadratic, we can solve the line search problem analytically as well. So here, if the steepest descent, but here I just it can be any method. But okay, here we just assume that the vector sk is the steepest descent. Okay, here we assume that we use the steepest descent with an exact line search. The exact line search means we find the optimum lambda. That is the lambda that minimizes by lambda that minimizes f sk plus lambda sk. Okay. Then we determine the optimum step length lambda k star for each step k, for each iteration k, So how can we do this? We'll do that analytically by hand. You don't have to, okay? And so here so we replace x by, we substitute x by xk plus lambda sk. And then we define a lambda, phi lambda, right? Phi lambda is defined as, just for convenience, we define phi lambda as fxk plus lambda sk. Okay? Then you can see that phi of lambda, then is equal to this, the whole expression. Right? And so how to find the lambda how to find lambda star, lambda k star, lambda k star. So we have to differentiate. We have to find the derivative of phi, right? And then set the derivative of phi to be 0 to find the lambda star. Okay. So from this you can see from the expansion of the expression phi of lambda, you can see that this is a constant term, right? It's a constant term. So that means when you differentiate a constant term, all the constant terms disappear from the derivative in the derivative formula, right? Then so what we have is already this one, and when we differentiate this one, don't forget that we have 1/2 multiply. Then we have this. Right? So we have this 3 terms left. Then we equate. Okay. Then we set the we equate this to be 0. Right? And then from that we solve the linear equation. We have only one variable. You can see here the lambda that is a solution of this is lambda is equal to minus sk transpose. Right? You can see that the lambda is equal lambda is equal to what? To minus s here transpose the qx, okay, plus, okay, minus again, minus of sk transpose qx, okay, plus e transpose xk divided by sk transpose qsk. Okay. In my writing, I use the subscript k instead of the superscript k, just for. So this is the formula for the optimum step size. Okay, for a search method. Okay, for a method that has the search vector sk. Then with the steepest descent, we know that sk is equal to minus squared fxk. Then we substitute this into the formula 5.10, and we have the answer. The final answer is here. This is the final answer for the steepest descent method. Okay. Now if for other methods we can substitute we can substitute sk, okay, by some, okay, we substitute sk with whatever in the formula. Okay, for the quasi-Newton or for the Newton method or for conjugate gradient, they have different formula for computing sk. That's all. Okay. Now we look at the convergence of this, how the method behaves. I think here we find that the steepest descent with exact line search generates the iterate xk that zigzag towards the solution. So how can we see this, right? Then I'll do, okay, I will illustrate this in a two-dimensional problem. In a two-dimensional problem, okay, in a two-dimensional problem, we can see that the trajectory of the iterate xk in a x1 in a two-dimension in a plane. Am I right? In a plane. So before we do this, let me draw a picture. In, let's say, in a three-dimensional, okay, in two-dimensional problem, if we can you can represent a two-dimensional with the fx used in a three-dimensional, right? The x1, x2 is for the domain, and then in the x-axis represent the fx. So how the function look like? The function looks like this, right? In a three-dimensional space, right? And this is the minimum, right? This is the minimum. Then there is a word called level set. Level set is defined as the set of x1, set of x in Rn, such that fx is equal to a constant. So what is it in this two-dimensional problem? To find a level set, we define a constant plane fx equals constant, right? Right? Once we set the fx equal constant, then this is a constant plane parallel to the plane x1, x2, right? And then it will cut the surface. And then when we project the surface onto the x1, x2, we have a contour. We have a contour. So any x1, x2 on the contour gives fx equals constant. Am I right? So in this so in this problem we can for a function with two variables we can project, okay, we can draw the level set on the plane x1, x2. That we can see what's going on there. Right. So when you cut this with a plane, my drawing is not very good. Okay, so that's why it's then when you cut that, it generates a plane, and we project this onto the x1, x2. Okay, project this. equal a constant C. Let's say C1. Okay, let's say C1. So when for a function f with two variables, then you can see that there are, when we draw the level set, what we will have is this. This is the minimum for x star, where we have the minimum value of the fx, right? Then when we draw this, the constant, the level set represent a closed contour on x1, x2. And this one, it's fx equals c1, for example, right? And we have another one, which is this one. It is fx equals c2, where c2 is greater than c1. Am I right? Yes. Okay. Now we will see what the steepest descent look like. Let's see. We may need another one, which is the. This is the fx, right, equals C3, which is greater than C2. Okay. Now, suppose the iterate xk is here. This is the iterate xk. Then what is the gradient vector? How can you find the gradient vector on the plane x1, x2? From third year calculus, we draw the tangent. Okay, this is the tangent. Huh? This is the tangent line or tangent plane in the Rn space, right? And then you draw a normal vector at this point, right? And the normal vector is this. Okay. Sorry. Then this is the search vector. This is the grad f. Okay, right? This is the minus grad fxk, right? Okay. Okay. So this is the search vector sk, right? Am I right? Because this is the gradient. This is the grad. This is the grad fx. Okay. Right? So we search along this. And then we search along this. Okay, let's see what happens when we search along this. When you search along this, what happens? Then the minimum along the green line, along the vector sk, is where it touches a level set, right? Yep. Okay, it touches am I right? At this point. At this point. At this point. So at this point, what is the, okay, at this point, so we know that from this xk, this is xk plus 1. Okay, this xk plus 1. Then how can we find the xk plus 2? Then we do that graph, okay? In this, we can do that by graph. We can do the steepest descent by graph, right? And then at this point, we find the SK. The SK is, you see the SK, right? I should use the blue, okay? This is the search vector SK plus 1 of the steepest descent, right? At this point, then what is the minimum? The minimum is where this direction, okay, when this direction becomes the tangent line, it touches another level set, which is this one. It can be that, right? So this is the vector xk plus 2. Right. Now you can see that here it generates the vector xk minus 1. Sorry, the vector sk plus 1 minus xk is orthogonal to the vector xk plus 2 minus xk plus 1. This vector. Okay. This vector. Okay, this vector is orthogonal to this vector. Okay. And now, what is this? The vector xk, the vector xk, the vector xk plus 1 minus xk is in fact equal to lambda k sk, right? Am I right? From the update formula, xk plus 1 is equal to xk plus lambda k sk. So if we move the xk from the update formula to the left-hand side, then we have xk plus 1 minus xk equals lambda sk. And in a similar way, we find that xk plus 2 minus xk plus 1 is equal lambda k plus 1 sk plus 1. Okay? And we, from the steepest descent property, we know that lambda k and lambda k plus 1 are positive, right, by the descent property. Okay, so when we do the dot product, that means the dot product of the two vectors eventually becomes lambda k plus 1 multiplied with sk transpose sk plus 1, right? Okay, this is what we know. Now this is how we arrive at here. Actually, this is quite straightforward, but I illustrate this so that you can see how the steepest descent proceeds. Okay, in real situation, in a two-dimensional problem. Okay, and so when first, then we have to prove that this is equal to 0. You see that when we use an exact line search in the iteration k, what is it? In the iteration k, Now we have to go back and write it. In the iteration K, when we do the line search in the iteration K, now you have to remember what we are doing. In the iteration K, so we move from xk to xk plus 1, right? Then when we do the line search, then at this point, this is a 0 and this is the lambda k star, right? This is the lambda k that we choose, right? We use exact line search. And if this is, we minimize fxk plus lambda sk, right? Because we start at the iterate xk. Okay? So when we find the lambda k star, the lambda k star, the gradient, the slope of fxk plus lambda sk is 0, right? At the optimum lambda. At the optimum lambda k. So what is the slope at this point? The slope at this point is sk transpose grad f xk plus lambda star sk, right? This is equal to 0. And what is the sk for the steepest descent? For the steepest descent, steepest descent method, sk equals grad fxk, right? And fxk plus lambda star sk is grad fxk plus 1, right? So you can see that now, for this, we find that the grad fxk plus 1 is orthogonal to the gradient at the point xk plus xk and xk plus 1. The gradient of fxk is orthogonal to xk plus 1. Okay, so that's the end of the proof. Okay, we will. So on Wednesday we will finish this. We will talk about the rate of convergence of the steepest descent and continue and look at the Newton's method altogether next time. Okay, bye bye.